Hey guys, so now we're going to go over how to find the area under the curve using a limit. So we talk about derivatives for a second. When we started taking derivatives, we would take the limit of a difference quotient and then that would give us our derivative. So it was very long and painful, and then shortly after we learned our derivative rules, which were like a nice little shortcut. Well, the same thing's going to happen with area. We first have to go through this definition in the limit form to find the area, and then we're going to learn our shortcuts, which are going to be called our nice indefinite integrals, right? So let's go ahead and get started. So here we have that we can approximate the area under the curve using a limit, right? And the formula that we're going to use, the recipe, is going to be this thing right here that looks kind of scary at first, but I'm about to break it down for you. And yes, I did notice that I put some rules here. There's some sigma rules because if you guys notice, our definition has a limit, but it also has a sigma in it, which is a summation rule. And these little shortcuts are going to become very helpful when computing our areas and computing our sigma limits. So let's start off by drawing a curve, and then we're going to show what the area under the curve is and how we're going to find it, right? So I'm just going to draw a curve right there, and I'm going to start off by finding from A to B, right? So I'm finding an area from A to B, and the way we're going to find area in this case is going to be through the use of rectangles, right? So when we're doing an area as a limit, what we're trying to do is we're trying to pack as many rectangles as we can so we can have a smaller error. So we're gonna go ahead and just kind of draw a rectangle. We're gonna pick some random point, some x value here, some x star. That actually looks like xx, but I'm actually gonna have like an x star here, and then I'm gonna try to draw a rectangle, right? So I need to have go up, and then just kind of draw like some kind of rectangle there. So I'm pretty much going to find a bunch of rectangles, find the area of all those rectangles, and then just add it together, right? And that's where the sigma comes in, right? So that explains the sigma part of my formula. A sigma means sum, right? Sigma sum kind of makes sense. And then we're going to have to find the area of these rectangles. But to find the area of a rectangle, I need to multiply the base times the height, right? So let's see how the area of a rectangle is going to translate to our formula. So for starters, what's going to be my base? Well, my base is actually going to be whatever this length right here is, right? Whatever this length right here is on the base of the rectangle, and that is going to be translated to the change in x. The change in x, we're going to think about it as the base. So now we're going to translate it as the change of x, right? And that is actually right here. So here we have our change of x, which is going to be our base, right? And now we need to talk about the other component, which is going to be the height, right? The height of your rectangle to find the area of it. And the height is just going to be at this point right here. I'm actually going to choose a thick red. That point right there is going to be the height. And that is where the x value hits the curve, right? And that is going to be our f, the f of x star. So let's kind of write that in blue. So this point right here is going to be our f of x star, right? Because f of x is usually the y, and the y is going to be our height. So when we multiply our change of x times our f of x star, that's going to give us our area. And if you guys notice, the f of x star is right here. So this component represents our height, right? So here we're multiplying, what this formula says, that we're multiplying the base times the height to find the area, right? So in essence, these two components are just going to give us the area. So what we're doing is the summation of a bunch of areas of a bunch of rectangles, and then the point of having the limit here is the fact that n is going to be our number. Our n here is the number of rectangles, right? So we're finding infinite number of rectangles, and then we're adding up all their areas. That's kind of what that is exactly what this definition says. We're finding the limit as n approaches infinity, which means that we have infinite number of rectangles, and then we're adding up all their areas, starting from the first one to the last one, which is going to be the infinite one. So that is going to be starting from 1 to infinity. So this means that we are going to have infinite number of rectangles, right? Because the more rectangles that we have here, the smaller our area is going to be and the easier we're going to approximate the area, right? So we're trying to find this area right here, the area under the curve, which I'm going to draw in highlighter yellow. And the way we're going to find that area is through the use of rectangles, right? We're going to draw a bunch of rectangles, and that is going to be a recipe, right? But this is going to be like the slow, annoying way to compute this. And then eventually, this is going to translate to a shortcut, which we're going to call the integral, the indefinite integral. And that is going to look like this. We're going to take this whole part right here, the limit of the sigma notation, all that, and that is going to be replaced with a very nice smooth curve called the integral, right? So when we introduce here the integral, we get rid of limits, right? Just so you guys make the relation between the slow sigma notation with the limit to the fast shortcut with the integral. So that is going to be f of x. So we changed that whole limit and sigma for the integral, and now our change of x, our f of x just came here. Nothing changed there. And then last, our delta x, or change of x, is going to be changed for dx, right? That's just a differential of x, or just change in x. So that right there is how we're going to go from the long, annoying, slow, painful definition of a limit, of the area as a limit, to the actual integral. So let's go ahead and get this started, right? So there's three different methods where we can estimate the area, right? So we can take the area estimating on a left point, on a right point, or on a midpoint, right? Because when we talked about here making some rectangles, you can make rectangles different ways. You could make a rectangle starting on the left, going up, hitting the graph, and then going right. Or you can make a rectangle starting on the right, hitting the graph, and then going to the left, right? So it's either or for those methods, right? So you can take either or of those methods, right? Which they are called a left endpoint approximation or a right endpoint approximation. And then the average between the two is going to be your midpoint, where you just go in between your rectangle. You go up, and then you go both left and right, and then you go down on both sides, right? So those are the three different types of approximations that we can have. In this example that I was starting to draw out and tell you guys about the rectangle and the base and the height of the rectangle, I told you guys that I was just going to go up, and I just started on the left. I didn't even tell you guys that I'm starting on the left. I just went up on the left. So then it didn't matter. But now here we actually have different types, and you guys can notice that we can do different types of approximations, right? For some it's better, for some it's worse. So let's focus on this left endpoint approximation and kind of discuss it and why we need a lot of rectangles, right? Let's emphasize on why we need a lot of rectangles. So let's say we only use 6 rectangles, right? What's gonna happen? Okay, so we're starting on the left, going to the right, so we're starting here again, starting on the left, going to the right, starting on the left, going to the right, starting on the left, going to the right, and so forth, right? So I'm going to go ahead and draw. I already drew all the rectangles, but you guys are seeing that I'm hitting the graph on the left endpoint, and then I am going to the right, right? So those are my f of x stars. So if you guys can see, I'm looking for the area that's the area under this curve, but there's a problem here, right? I have all this like leftover. I'm going to do it in blue. I have all this dark blue area which isn't getting covered, right? So this right here is not getting covered. This right here is getting over covered, right? It's getting over covered. This right here is also getting over covered. So is this. So is this. And so is this, right? So these are different types of problems, right? So here, in this type of scenario, right, where my graph, the whole graph isn't covered, this is going to be called an underestimation, an underestimate, right? So I'm underestimating my area. And when, for example, when my rectangle here covers too much, this is called an overestimation, right? So the idea, overestimate. So the idea is that since I only have 6, my underestimation or my overestimation is just a lot. I have a lot of error, right? So I need to get rid of all this error that I have. And the way to get rid of the error is by adding more rectangles, right? So the more rectangles that I have, the less error that I'm going to have, because I'm going to have less overestimation or more less underestimation. So that is the whole point of adding more rectangles, right? So the same thing's going to happen. We're going to have a bunch of error. I'm just going to go over real quickly here. You guys see how there's error everywhere. So in some terms, you guys can even see that the midpoint still has error. You may think it's a little better, but you still have error everywhere. So what we're going to do, that's where the whole limit as n approaches infinity comes in, because we want to add the most rectangles possible, right? And now we're going to go see how we can apply this to an actual problem, right? So I'm going to give you guys an example where I just say, hey guys, find the area under the curve of this function over this interval. And then we're going to bring in some stuff. So one last thing actually before we go into the example is the thickness of the rectangles, right? The thickness right here matters, right? So how thick your base of the rectangle is, that is just another way of saying the base, and we said that the base of the rectangle was equal to the change of x, right? So your base of your rectangle is equal to your change of x. So keep in mind that the smaller your change of x is, right? The smaller the base of the rectangle is, the better your approximation is. And that is why we choose the change of x to be really, really, really small, and we try to have infinite number of rectangles. And you guys will see how the infinity affects your change of x in just a second. So here I'm going to ask you to find the area under the curve of f of x, which is x squared plus 1 over the interval from 0 to 4. And I'm actually going to make this even simpler. I'm going to tell you just to find the area under the curve of just x squared over the interval from 0 to 4. So this right here is going to be our a, this here is going to be our b, right? Our starting point and our ending point. And then we're going to go ahead and get started on the approximation. So when I tell you guys to find the area of this over this interval, we're supposed to use this really long limit with sigma notation. And the way we're going to do that is by, first we're going to write the actual formula. So the area is going to be equal to the limit as n approaches infinity of the summation starting at 1, ending at infinity, of f of x k star times delta x. Okay? And the first step that we're going to take to putting all the pieces together of this formula is going to be finding delta x. And I never actually gave you a full definition of what delta x was, but delta x is going to be the width of the interval, right? And how you find the width of the interval is going to be by subtracting the b minus the a, which is the whole range, your whole range of the x, b minus a, and then we're going to divide it by n, which is going to be the number of intervals, right? So you're going to see what the length from a to b is, so we can just see it, for example, right here. I just highlighted the a to b, right? So that length right there from a to b, and then I'm going to divide it by the number of intervals, which is going to be n, right? So that's why I always want my n to go to infinity, because I want to have the most number of intervals possible, which gives me the most number of rectangles. So in that case, we never actually know the n. We leave the n in terms of n so we can apply the limit after. And what that means is that first I'm going to use my interval from 0 to 4. So it's going to be 4 minus 0 over n. I never actually put a number of interval because I am approaching a limit. So I'm going to have 4 over n. And then after my change of x, I go ahead and I find my f of x star. So I'm going to find f of xk star. And what I'm going to do there, I'm going to plug in my x star into my xk star into my actual function, right? So I'm plugging in my xk star, and that's where the actual type of approximation comes in. I'm doing a left endpoint approximation, so I need to use this xk star. So I need to use a plus k minus 1 times delta x. So I'm using a plus k minus 1 times delta x, right? So I need to actually use my delta x in my x of xk star, so that's why I compute it first. So if I start off with plugging in my a in this problem is 0, so I have 0 plus k minus 1 is going to stay in terms of k, and my change of x, well, this is actually all supposed to go to the second power because I'm plugging in my xk star into my function. So I'm plugging in this x into my function, right? So this whole thing is squared. So let me go simplify. My a is going to be 0 plus k minus 1. Delta x is going to be 4 over n, and this is all going to be squared, right? So if I kind of clean this up, I'm going to have f of x k star is going to be equal to 0. Is not going to matter, and I'm going to need to apply this second power, right? So the k minus 1 is getting squared, and the 4 over n is getting squared. So I'm going to get a 16 over n squared because I square the 4 and I square the n. So after I do that, I already have my delta x and I have my f of x k star. I'm ready to put it all together into my equation of the area. So once I do that, I'm going to write a is equal to the limit as n approaches infinity of the summation starting at 1 of f of x k star, which I told you that is k minus 1 squared times 16 over n squared times delta x, right, which is going to be 4 over n. So I hate writing the limit as n approaches infinity over and over again because it just takes up a bunch of space. So I'm going to kind of ignore it. But there's two things that I need to do. I'm just going to write my area, and then I'm just going to just bring it down. I need to simplify this guy right here, the k minus 1 squared, because that is k minus 1 times k minus 1. So that's like I have to FOIL. And I'm actually going to do it up here to save some space down there. So if I distribute, I'm going to get k squared minus k plus 1, leaving me with k squared minus 2k plus 1. So that means that there I'm going to have k squared minus 2k plus 1, and then I'm also going to multiply these two guys together, leaving me with a 64 on top and an n cubed on the bottom. Okay, and then I can also go ahead and multiply out, I can go ahead and distribute this guy times all my terms. So I'm trying to get the most individual terms possible in this problem. So I'm going to have my area, and then it's going to be equal to 64k squared over n cubed minus 2 times 64. 2 times 64 is 128k over n cubed, and then 64 over n cubed times 1 is just going to be plus, right? And now I need to actually bring back my limit, my last set that I apply in the sigma from 1 to infinity, because now here's where I actually apply my rules. And by my rules, I mean that I'm going to apply these little guys that I have up here, right? So if you guys notice, these are all limits, and they're starting at 1 and they're going to n, just how I have my limits right here. And they're going to help me actually find the answer, right? Because I have no idea what the limit as, actually this goes to n. The limit of 64k squared over n cubed, like I have no idea what that is. So I'm going to use my shortcut equations to help me get there. And there are 4 equations. They're very simple to memorize, and it's actually take 1 second to go back over there and see how they're really easy to memorize, right? So here I have 1 over n outside, and I just have a 1 here, and it gives me 1, right? So this one won't make too much sense until we go over the next one. And the next one I have 1 over n squared, the same thing, the sigma, and then I have a k, and then it gives me 1/2. So here I have an n squared, and then I get a 1/2, right? Now in the third one I get 1 over n cubed, and my answer is of k squared, and it gives me 1/3. And if you guys see the last one, it's 1 over n to the 4th, and the answer is, you have k cubed here, but the answer here is 1/4. So the idea is that the exponent of the 1 over n in front that you can take out is going to be the denominator of your answer, right? So here you have 1 over n to the 1, so it's 1 over 1. Here you have 1 over n to the 2, so it's 1 over 2. 1 over n to the 3, 1 over 3. 1 over n to the 4th, 1 over 4th. But keep in mind that you do need to have a k that has 1 power less than your exponent of the n. So it's a little tricky, but once you guys use it a few times, you guys will get it just fine. So let's go back down to talking about this problem, in which actually it's gonna be a little annoying, but I had to split it up into three different sigma notations, right? So I'm actually going to rewrite this guy 64 over n cubed. I'm going to rewrite him over here, so then I can stick a sigma in front of it. Oh, that's to the n. And then I'm going to go ahead and, the limit is applying to everybody, by the way. I'm just going to change up the sigmas. And then I'm going to go ahead and move this guy, this 128k over n cubed. I'm going to go ahead and move this guy a little over here. So 128k over n cubed. I'm just moving him over here. You guys have a little more space down there in your paper, but I'm a little limited here. Up to the n. Keep wanting to put infinity there. So this is what we're going to do, right? We have, the way I'm going to play out this game is that I have a k squared, right? So I have a k squared. The k squared matches with an n with 1 power greater. So that n with 1 power greater is going to be an n cubed. So the way that I'm going to rewrite this is going to be that I'm going to go ahead and take out this n cubed outside, right? So I even have a little bit of space to play around here. Actually, I have a good amount of space here. And I'm going to go break up all these terms, all these three terms, right? So the first term, I don't like it there. So I'm actually going to, so I'm just going to write it down here. I'm going to be real short on space, but you guys will be better off if I just write it all straight. So limit as n approaches infinity. You guys actually can't see that, so okay. So I'm gonna be stuck doing it up here. So the first term, I'm actually gonna take out. I'm gonna take out the n cubed. If you guys see, I'm gonna take out the 1 over n cubed. I'm gonna have the sigma k to the first to the n, and then I'm gonna have. I'm also going to take out the 64 as a constant, and then I'm just going to have a k squared, right? So if we go up here to our rules, whenever I have a k squared and whenever I have a k squared and an n cubed, the answer is going to give me 1/3, right? So I'm going to go back down. So I'm going to go back down here. So this whole answer right here gives me 1/3. So my answer will be 64 times 1/3, or 64 over 3. All right. Then the other guy, it's going to be a minus, and then the other guy, I have an n cubed. And then I have a k. Well, those don't match because I need a k squared to go with my n cubed. Therefore, since the n is much bigger than the k, that whole term is going to go to 0, right? So if they don't match, right? If your k does not match with your n, the whole term is going to go to 0 because your n is bigger. So you are taking a limit, so when the bottom is bigger, you are going to go ahead and make it the whole term equal to 0. So the second term is going to go to 0. So this whole term is going to be minus 0 because the n is bigger, so the whole term goes to 0. Okay? And then you guys see over here, the third term doesn't even have a k, and the bottom is an n cubed, so the whole term automatically itself is going to go to 0 as well. So and it's going to be a plus 0. So our only answer, our final answer from this answer is going to be 64 over 3. So our left endpoint approximation is going to be 64 over 3. I know it's a lot of messy work, and it's real annoying, But after we get all this done, we can just go straight into integrals, and we never have to do this again, right? This is just in case your professor wants to go ahead and throw some of these sigma notations. And the sicker your professor is, the more he likes this. So come on, they're going to be coming. So now we're going to do some right endpoint approximations in letter B. And the only thing that's going to change in this problem is going to be the fact that our xk star is going to change, right? So we're going to start off the problem the same. I'm not even going to rewrite this. I'm not even going to rewrite the area equation because I'm going to use it again. So I'm just going to leave it right there. So we're going to have a little more space here. Our change of x is going to be the same, but let's just do it one more time because we start off by finding our change of x. So let's go ahead and do that. My change of x is going to be b minus a. I have the same interval, 4 minus 0, b minus a. So let's go ahead and highlight that. It's another important formula here. b minus a over n. So that's 4 over n. So that gives us our change of x. After we find a change of x, we need to go ahead and find our f of xk star. And how we do that is we go up here. And we just get our xk star. It's going to be our right endpoint, right? So we're going to use this guy right here. So we're going to use f of xk star, which is going to be, our function is squared, so we're plugging in this guy into here, and that means that we're going to have a plus k change of x squared, right? So it actually becomes a lot easier because we don't have the k minus 1. And you guys will see how much simpler this example B actually is. So in f of xk star, we go ahead and kind of like clean it up just a little bit, xk star. We're going to start off by inputting our a. Our a in this problem is going to be 0, so it's going to be 0 plus k. Our change of x simply comes from here. That is going to be 4 over n, and then this whole thing is squared, right? So the 0 doesn't matter, so we're just going to distribute this squared to both this guy and this guy, because the 0 just doesn't matter. And then we're going to have our f of xk star is going to be equal to, k squared, right? And then it's going to be equal to k squared, and then we're going to have, the 4 squared is going to be 16 over n squared. So we're done computing our f of x k star. And now we're ready to put it all together in our third step into our area function, right? So yes, we need to start off with the limit. I know it's kind of annoying, but let's just go ahead and get that done. So after we have that, we need to just have our f of xk star, which is going to be this guy right here, number 2. It's going to be k squared 16 over n squared. And that is all going to be multiplied by our delta x, which is 4 over n, right? So we just finished this part, and now we're going into this part. So once we do that, we need to go ahead and find, I'm not going to actually rewrite the limit. I'm going to be lazy. And I'm just going to distribute just a little bit, right? So I'm going to multiply these two guys. So I'm going to get a 64k squared. And then if I multiply these two guys, I'm going to go ahead and get an n cubed. So if you guys see how this one is actually much more straightforward because I only have one term compared to 3 terms, right? And if I go back to my rules, I have an n cubed, so my k needs to have 1 power less. So I'm looking for a k squared. Which I have. So all I really need to do is just rewrite this one more time. I'm going to have my limit outside right here. I'm going to bring the n cubed and the 64 out. So I'm going to have 64 over n cubed outside with a summation starting at 1 going to n of k squared. So that means that this whole term right here, according to my rules, my little shortcut that I give you guys on the top of this page, is going to give me 1/3. So the whole answer is going to be 64 times 1/3 or just 64/3. So this shows that our left endpoint approximation and our right endpoint approximation are exactly the same. Obviously, the right endpoint approximation was way less painful than our left endpoint approximation, but we showed how to actually deal with when we have more terms compared to when we have less terms, right? So I think you can benefit more from the left endpoint because you get to see a lot more of the whole sigma solving and all that stuff. So now that's it for now, and I'll see you guys next time.